What is going on today? Just leave that on for a couple minutes. Drinking my coffee. It's like the best song ever. Why is the chat still messed up on this thing? I swear. Looking for your top 3 favorite TV shows of all time. Type it in the chat. We'll get rolling here in a couple minutes. Need a better song. See what I got here. Alright, we're going to start in about another minute. Anybody wants to answer the question of the day is, what are your top 3 favorite TV shows of all time? Type it in the chat. Office is a good show. I might have to go back and revise my TV shows. Anything else? Oh no, we don't need to hear this again. Top 3 favorite TV shows of all time. What are they? So we got The Office. Office is a really good show. Alright, while you guys are typing, let me go through mine. Alright, so, no judgment here. Star Trek Voyager. Love that show. It's my favorite Star Trek series of all time. The new ones are pretty cool, but I'm still a big fan of that specific series. I actually met Kate Mulgrew, who is the captain in that show. She did a book signing at a bookstore in Naperville. Was it this year or last year? I don't remember. One of the nicest people I've ever met. She's awesome. So Star Trek, huge nerd, I know. Futurama, it's another show that I absolutely love. It's a cartoon if you haven't seen it. It's created by the guy that does The Simpsons. Main character in the show gets frozen and then shows up in the future. So definitely down with Futurama. I want to get frozen, and I'm going to get a robot in the future to be my friend. So that's my plan. That's my life goal. And then Breaking Bad. Yes, I teach chemistry, and I'm bald like Walter White and have a goatee and wear glasses, but I don't make meth. Don't do anything bad in chemistry. I'm a rule follower. I'm like the anti-Walter White. So anybody else want to chime in? What your favorite TV shows are? Just The Office. That's all we got so far. Okay, well, yeah. Walter White's pretty cool, though. I don't think that I could be as cool as him. I'm not even close. My kids tell me all the time that I'm not cool. So, anyway, let's keep moving along here. So, if you haven't done so already, make sure you do that Google form check-in. I'm going to pretty much bug you about this every day. Hey, Jeremy, how's it going? I'm going to bug you about this every day. It's just my way of checking in with you guys to make sure that everybody's doing okay. See if you guys have any issues with e-learning. If you're having any issues with your computer, The help desk is taking requests right now. They'll I don't know if they'll call you or what the situation is, but I had a student yesterday that was having issues with her laptop, and she was able to get help through them. So if you run into any problems with your computer, reach out to the help desk, and they can get you guys hooked up. Okay. I also heard that they are also doing drive-up service, so you don't have to go into the building. So if you just take your computer and email them in advance, they'll swap your computer up. All right, so before we get into anything physics related, I saw this on Twitter this morning, and let's see if you guys can figure this out. So this is a graph that Fox News had on. It's the number of new cases per day of the coronavirus. And let's see if anybody can look at the graph and figure out what is wrong with the graph, because there is something majorly wrong with this graph. And I was a little surprised that a news station had a major error like this on their graph. So it might be a little small on your screen, but see if you can figure this out. Give you a couple minutes, or I'll give you like 60 seconds before I go through it. So take a look at the graph, tell me what's wrong with it, because there's a major problem with this graph. It took me a while to figure it out, but then once I figured it out, I'm like, oh my gosh, how could they do that? If it's too small, I'm sorry, but you should be able to see it still. It's a pretty obvious mistake on this graph here. Anybody see the issue yet? I should put some music on. I should put the Jeopardy song on while you guys are thinking here. Let me see. Oh, here we go. Anybody have the issue? What's wrong with this graph? Anybody want to chime in for... I wish I could give you guys candy right now, but I can't. Anybody see the issue with this graph? All right, the issue with this graph, nobody chimed in. The issue with this graph is right here on the y-axis. So if you look down at the bottom, you'll see that it starts at 30. It's not that big of a deal. So it goes 30, 60, 90. So those are pretty consistent, right? But then it goes from 90 to 100. So 30 to 60 is a difference of 30. 30 to 90 is a difference of 30. All right, but then 90 to 100 is a difference of 10. And then going from 100 to 130, that's 30, then 30, then 30. Going from 190 to 240 is a difference of 40. And then going from 240 to 250 is a difference of 10. All right, and then 50, 50, 50. So this graph is all over the place, right? I would just put a big red X through that if I was grading somebody's paper, because that's terrible, right? Why does that matter, though? Why does the y-axis, why does it need to be spaced out consistently? I'll tell you why. So I took the numbers off the graph, and I created my own version of this graph, all right? And here it is. It looks relatively similar to the graph that you just saw. However, when you go to do a trend line, when you go to extrapolate what the number of new cases might be in the future, if you have the scale all wacky, it's going to totally mess up your predictions. So you can totally take a graph and you can make it look completely different just by messing with the scale. So shame on that news station. They would have gotten an F on their graph. Maybe a D. Maybe a D. I don't know. We'll see. It depends what kind of mood I was in when I was grading that day. Okay, so let's talk about this week. Wednesday's the deadline for the test. So if you took the test already and are happy with your grade, you're done. You don't need to worry about the test anymore. Today we're going to do data collection for the lab, those of you that are doing it with me. And I'm going to go through how to do everything in just a couple minutes. Tomorrow we are going to do some graphing. So that'll be kind of exciting, right? Your graph's not going to look like this one, though, right? Your graph's going to look totally better than this. All right, so we'll do a graph on Wednesday, and then Thursday we're going to write our claim and our reasoning. So if you keep coming back and watching on YouTube, I'm going to go through every single part of this with you. You just basically have to follow along with me. That's it. I also want to remind everybody on Thursday we're going to do our Zoom chat instead of Friday, because Friday we don't have school. We don't have e-learning that day. All right, so let's take a look at the simulation here. Let me pull it up. I forgot to link the simulation yesterday in the post, but I did put it in there today. So let's go through this. So you've got your battery, right? You've got your resistor, and let's go ahead and wire this up. Try not to blow anything up. Okay, so hopefully you know how to do this. And then we are going to set our resistor to 25 ohms. And you do that just by clicking on it. Down at the bottom here, let's change the resistance to 25. All right, so we got our resistor in there, and we're trying to explore the relationship between voltage and current in this lab. So to measure current, we need an ammeter. So we'll bring one of those out, and then we're going to place the sensor. Look at this. This goes all over the place. This is so much fun. We're going to put the sensor right on the resistor. Okay. So in the lab document, in OneNote, let me clear this up. In the lab document in OneNote, you have the evidence section and you have this table. You have to go in and change the heading on the table here. So I don't remember what it was defaulted to. It was like independent variable, dependent variable. So our independent variable, the variable that we're changing is the voltage. So when we click on the battery, we can change the voltage. So that's the independent variable. So again, back to our lab document. This first heading should be voltage in volts. And then the dependent variable, the variable that we're measuring, is the current. So this up here should say current for both of these trials, and then the units of current are amps. Okay, now if we were actually doing this lab with an ammeter in class, which looks like this. Oh, that's a really old school one. They have digital ones. So they look something like this. If we were actually doing this with a real circuit and we were measuring these out, the readings might fluctuate a little bit. So if we were actually doing this lab, we might get different variables, but because we're using a simulation for this, because we're using this, the values are going to be the same. All right. So if I go to like 17 and then come back, it's still 0.66. Still 0.66. It's still 0.66. Okay. So you don't need to do, I mean, there's a spot there for more than one trial just because we could have used this lab for an actual circuit, but whatever you measure is going to be the same for both trials and then for your average. All right. So I'm going to throw in some numbers here, and you can pick whatever numbers you want. It really doesn't matter what you pick. So this is what you're going to do. So what do we have this at? 16.5 volts. So 16.5 volts. And the current is 0.66. 0.66. So I'm going to fill that in. Oops, 0.66 everywhere. Done. Let's do another number. What number should we pick? How about, let's do 100 volts. 100 volts. Look at the electrons going crazy in there. So 100 volts gives us a current of 4 amps. So 100 volts gives us a current of 4. All right. Okay, and let's do another one. Let's do, oh geez, I don't know. How about just not pay attention, close my eyes, and 109.5. So 109.5 gives us a current of 4.38. 4.38. Done. That's literally all you have to do today. So pick 3 voltages. Don't pick mine. Pick 3 different voltages, and then write the currents in the boxes. That's literally all you have to do. Okay? Tomorrow we're going to throw these into a graph. Tomorrow's going to require a little bit more work, but today actually won't require any work because you're not moving. Yes, I'm going to keep using that joke for the rest of the year now that you guys know what work is. So, pick 3 voltages, measure the current, throw it in your OneNote. That's all you have to do for today. What questions do you guys have? If you don't have any questions, I was going to play OregonTrail for the next 15 minutes to keep myself occupied until chemistry. You guys are welcome to play along with me if you'd like. I tried playing that, what's the name of that game? The circuit game. Nobody really liked that game when I played it, so I thought I'd play a game that would be a little more entertaining. Either you guys don't have any questions, you're not paying attention, or I don't know what else. You're either not paying attention or nobody has any questions. I'm going to go with you don't have any questions. Alright, so I'm going to go ahead and close this up. And that's all I had for physics. I was not paying attention. I appreciate the honesty. It's just like regular class. You guys are all on your phones, you know, like this while I'm trying to teach. So I appreciate that. Alright, so I'm going to play a game. Well, I'm waiting for chemistry. If anybody has any questions, certainly. Why is this not going full screen? If anybody has any questions, well, come on. There we go. If anybody has any questions while I'm playing, feel free to just chime in. But I'm going to just play this game and pretend like I'm doing something so I don't have to do any other science right now. Okay, so this is the OregonTrail. It's a fantastic game. And I'm going to go ahead and play this for the next 15 minutes. I'm going to try to make it to Oregon. And we are going to travel the trail. This is like the game from when I was a kid. And they used to have teacher on here, but teacher is not an option. Let's be a farmer from Illinois, right? Who is the name of the wagon leader? Mr. Zorn. Okay, who's in the party? Let's see, who's in the chat right now? So we have Sarah, right? I saw Jeremy. Anthony was in the chat. Is there anybody else in the chat right now? I need one more name. Who could I use? I need one more name. Anybody want to chime in with a name? I'm probably going to be the first one to die in this game. I'm going to use my cat's name. My cat. This is my cat's actual name. Poopy. Alright. Are those names correct? Yes. Let's see. It's 1848. Your jumping off place for Oregon is Independence, Missouri. You must decide which month to leave Independence. March, April, May. Well, it's currently April, so let's do April. Before leaving Independence, you should buy equipment and supplies. You have $400 in cash. Don't have to spend it all now. Let's spend it all now. Alright. Yeah. Alright, we need oxen. Okay, how many oxen do we want? 2 oxen in a yoke. I'd recommend at least 3 yoke. So 3 times 2. See, we are doing science right now. 3 times 2 is 6. But, you know, let's get some extra ones. Let's get 8. Alright, so we've spent $320. Let's go back to food. We only need 50 pounds of food to, you know, get out here. Then I'm going to go hunt and get some more. Alright, clothing. We have, what, $70 left? Each set of clothing is $10. 2 sets of clothing per person. There's 5 of us. That'd be 10. We're going to have to wear the same clothes the entire time. So let's get 5 sets of clothing. Let's see, I have $20 left. Let's buy some ammunition. Let's see, 20 bullets, $2. How many boxes do we want? How about 10? Look at that. We spent all $10. We don't need any spare wagon parts because we're not going to break down. And boom, let's do it. The music in this game is the best. Alright, continue on the trail. Alright, let's do some hunting. Number 8. Spacebar. Oh yeah. I don't remember how to walk. Oh, gotta get the bear. Gotta get the bear. Or buffalo. Look at that. Boom! Oh, they're all over the place. Alright, I gotta be done hunting because I'm gonna run out of bullets. Look at the even the character in the game looks like me. Bald. Not sure why it hasn't gone to the next screen yet. I just wiped out like a whole forest. Look at that. I shot 926 pounds of meat, but I was only able to carry 100 back to the wagon. Should have brought the wagon over to the animals and just loaded them up that way. Not thinking very much. Let's hunt one more time. I gotta load up on food. A buffalo. Right off the bat. Look at that. I'm gonna go walk around, scare the animals. Kind of stuck in the woods here. Can't really go anywhere else. I'm stuck in this little corner. It's bad designing right there. Anybody else have any plans this afternoon? Going for a walk? It's really nice out. 833 pounds. Let's hunt one more time. Gotta load it up. I think I killed all the animals. Oh, he got away. Oh, it's a buffalo. Not doing so good. Oh, jeez. I feel like a failure. Alright, let's continue on the trail. Alright, so here's we gotta use a little bit of science. Would you like to look around? No. Okay, so the river is 3.9 feet deep. Do we try to walk across or do we try to float our wagon? We don't have enough money for the ferry because I spent it all on food and supplies. So, caulk the wagon and float. 3.9 feet is pretty deep. That's like half. That's like 4/6 of me. 4/6 is what? 2/3. I think we're gonna have to float. So that is floated across. Number 2. I'm probably gonna die here. Cross your fingers. Oh, we totally made it. We totally made it. We're good. You had no trouble floating the wagon across. Let's continue down the trail. Alright, we need to hunt again. It's my favorite thing to do in this game is hunt. Alright, here we go. Oh, a deer! Look at that. I gotta make my own sound effects. Oh, look at that. 2 deer. And there's a buffalo. Can't get to him in time. I'm not going to even waste my bullet on a bunny. Alright. We need to change the pace because I only have 7 minutes left. So we need to go to a grueling pace. And let's roll. Gotta go faster. Go, 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 go. Would you like to look around? No. 2.7 feet deep. We could totally just... We're going to ford the river this time. We're just going to walk across. This could be bad. Whew. I think we made it. Look at that. Supplies got wet. What the heck? This game cheats. Alright, here we go. This game needs some like background music while you're going. Oh, we're running low on food. Would you like to look around? No, we don't have time for that. Oh, blizzard. It's April 20th. How is there a blizzard? Alright, we gotta hunt again. Alright. Oh, 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 look at the buffalo. Oh, shot him. Best hunter in Oregon. Actually, I don't think we're in Oregon right now. I don't even know where we are. I really wanted to waste that other buffalo, but I'm not going to. Whoa, I'm going to get dizzy. How am I doing? Anybody paying attention still? 995 pounds of food. Continue on the trail. Totally going to get us to Oregon. I don't even know where we are right now. Is there a way to see the map? Sarah's paying attention. Sarah, you have not died yet in the game yet, so it says our health is fair though. That's not a good sign. When you get into fair, it's usually like downhill from there. Would you like to look around? No. Chimney Rock. Space bar. Here we go. Oh, we got to hunt again. Hunting for food. Oh, there's a deer. Oh, I missed him. Where's the buffalo? This is not good if we can't get food. Oh, I don't want to go home empty-handed. This is not good. We're going to have to adjust our rations if I can't hunt and find food. Alright, here we go. Oh, no! Ah, phew. Goodness, that squirrel's going to have to last us for days. You're going to be able to eat like a little tiny piece of squirrel. Oh, look at the deer. No, 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 no. Okay, nobody's paying attention. You can't see what a terrible hunter I am. Oh, look at that, 2 squirrels. The like person's fit 3 pounds of meat. That has to last us until we get to Oregon. So we need to change the food rations to like, let's see, bare bones. Meals are very small. Everyone stays hungry. We're gonna have to do that. Hey Daniel, how's it going? I'm just wasting time until chemistry pops up. So I'm gonna play OregonTrail for about 3 more minutes. All right. Nobody in physics had any questions. We are out of food. You passed a gravesite. Would you like to look closer? Yes. Voland. Hey, hey, come out and play. That's super, super creepy, right? Alright. Oh, wait, I have Daniel and Sarah in chat at the same time. Poopy's my cat's name, by the way. Poopy has a broken leg. Sorry, Poopy. Alright, let's keep going. Would you like to look around? No, we need to hunt because we have no food. And then I should probably start chemistry. Look at this deer. Like the Terminator. Oh, shot him. Ah, look at that. I'm going to get this buffalo too. Look at this. That is 5 animals right there. No, full disclosure, I'm actually a vegetarian, so I won't be eating any of this meat. 1,100, almost 1,200 pounds of food. That is some pro hunting right there. All right, let's continue on the trail. I think we got 2 minutes before I have to switch to chemistry. It says health is poor. That's not good. Not good. We have 80 pounds of meat. Go, 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 go. I'm trying to make it to Oregon before I have to teach chemistry. Find wild fruit. It's good for me. Vegetarian. Spacebar. Uh-oh, Sarah. Sarah, you have cholera. I don't know how you cure that. Let me look on Wikipedia. That's a reliable source, right? Where's my mouse? Cholera. Cholera. Let me look this up. Oof. This is not good, Sarah. Look at this. Let's see. It's an infectious disease that causes severe watery diarrhea, can lead to dehydration and even death if untreated. But I'm out of time, so unfortunately, you're just gonna have to hold on for some time while I teach chemistry, and then we'll come back and see if you make it. If I don't have time to finish this game, I'll have to pick it up tomorrow. But sorry about the watery diarrhea. All right. All right. So rolling over to chemistry here, because I have Daniel Carter, like a celebrity in here. What are your top 3 favorite TV shows of all time? Top 3 favorite TV shows of all time. So type them in the chat. What are your top 3 favorite TV shows of all time? I'm going to get my Surface ready to go here. Feel free to just type in the chat your favorite TV shows of all time. Top 3 favorite TV shows of all time. While you're doing that, I'm going to get OneNote set up here to go through some chemistry problems. Anybody? Daniel, what are your favorite TV shows of all time? I'm going to try to guess yours. What would Daniel be into? You seem like you would be... I would not have guessed any of that. I don't even know what... I've heard of Boondocks before. Never heard of Adventure Time and The Regular Show. Regular Show. Oh, it's a cartoon. Boondocks, Adventure Time. Let me look that up real quick. Oh, I've seen like Adventure Time, but I haven't like watched Adventure Time. All right. Well, let me share mine, and then we'll get into some chemistry practice. So my top 3 favorite TV shows of all time: Star Trek Voyager. Of all the Star Trek shows, it's my favorite. I know I'm a huge nerd, and I was saying earlier when I was talking about this with my physics group, I actually met Kate Mulgrew in person. She plays Captain Janeway on the show. She's one of the nicest people I have ever met. She came out to do a book signing at a bookstore in Naperville, and I was expecting her to spend most of the time talking about Star Trek, which is the TV series that she's famous for. But she wrote a book on having one of her parents had Alzheimer's, and she spent a lot of time talking about that disease and how it really affected her relationship with her parents. And there were people there that were in a similar situation, and it was just very touching how much time she spent talking about that and how she reached out to the people in the audience. So just one of the most wonderful people in the whole wide world. Now, William Shatner, on the other hand, I met him in person, and he was not very pleasant at all. He plays Captain Kirk, who's one of the famous Star Trek captains. Anyway, Futurama. Love that cartoon. Made by the same guy that wrote The Simpsons. It's not on the air anymore, but it's hilarious. And I'm planning on getting Frozen, and when I wake up in the future, I'm going to have a robot as a friend. Those are my goals. And then finally, Breaking Bad. Love that show. So for those of you that haven't seen it, it's about a high school chemistry teacher that becomes a drug lord. He produces meth, which is bad. Like, if there's one message that the show had, it was that dealing with drugs is just not a good idea because things just don't work out well for him. So, anyway, those are my top 3 favorite TV shows. All right, I'm going to keep bugging you guys about this every day. If you haven't done so already, there's a Google form. Check in to fill out. You should be doing this once a week, and I will send out a new Google form every week. So if you did the one last week, that's separate. I need you to do this one for this week. It's just how I can check in and stay current with you guys. So if you're having any issues with e-learning, or if there's something going on at home, like, somebody's sick, or, you're having to watch your siblings because your parents are working, whatever the situation may be, just let me know. Totally willing to work with whatever is going on at home right now. Just let me know so I'm updated. All right? Okay. So if you were here for the physics session, don't chime in. But for anybody that's just joining me right now, which I think is it's just Daniel, which is totally fine. Daniel, you are a gem. Let me tell you, I really enjoy having you in my chemistry class. So take a look at this graph. This is a graph that Fox News put out. It's of the new COVID cases per day. So on the x-axis, you have the dates going from March 18th to April 1st, and then on the y-axis, you've got the number of cases per day. But there is a major problem with this graph. So take a look at the graph and see if you can figure out what the issue is with this graph. It took me a while to figure it out. Another science teacher I know posted this on Twitter, and I grabbed it because it's good to talk about. So I will give you about a minute or so to take a look at that, and while you're doing that, here is the Jeopardy song. See if you can figure it out. Oh, we don't have to listen to that again. Alright, so nobody chimed in. You're either not paying attention or you couldn't figure it out. The problem with this graph is the y-axis. So if you look at the y-axis down at the bottom, It starts at 30. It goes from 30 to 60, which is a difference of 30. 60 to 90, which again is a difference of 30. But then over here, going from 90 to 100, that's a difference of 10. 100 to 130, difference of 30. Difference of 30. Difference of 30. 90 or 190 to 240 is a difference of 50. So then 240 to 250 is a difference of 10. And then 50, 50, 50. So it goes, let's see, 30, 30, 10, 30, 30, 30, 50, 10, 50, 50, 50. So the y-axis is all messed up. I don't know who made this graph for Fox News, but they did a terrible job. Now, graphs can certainly be manipulated to give you the wrong information. You can distort all sorts of graphs to make them look like you want with actual data. So what I did is I took the data off this graph and put it in Excel and made an actual graph that's accurate, and it looks like this. So on the graph here, it takes a very similar shape. So let me flip back and forth. So here's the graph from Fox News. Here's my graph. So they are very similar in shape. However, if you were to go and do a line of best fit, do a trend line, you would see that it's not going to yield the correct, it's not going to give you a good prediction because your y-axis is all screwed up. So when we do a trend line, it's a line of best fit, and we can just continue that line. Let me see if I go the right way. We could just continue that line forever, and it would give us a good prediction of how many cases we would have per day in the future. But since the y-axis on the Fox News graph is all messed up, it would give you an incorrect prediction. Well, I guess you can't really have an incorrect prediction because you're making a prediction, but it would be a lot less accurate. So I found that very interesting that they had a graph with obvious errors like that on their show. I mean, I think they would have been better off just like not putting numbers on the y-axis. All right, so for chemistry, as I said on Monday, we are slowing down significantly. All right, the pace of the class you'll find is going to slow down a lot compared to what we were doing before. So yesterday I posted a screencast with the single step calculations, and there was a Google quiz. Yesterday during the live stream, I went through all the answers for the Google quiz. We worked them all out together. So you can go back to yesterday's live stream and watch that to get the answers, or you can try to work them out yourselves. I'm going to go through another set of practice problems, which are very similar to what are on the quiz. So if you didn't quite understand how to do the math, we'll do it together. Tomorrow we're going to go through the next lesson, which is a little more complicated, but I mean it's still not too bad. Stoichiometry is the hardest thing I think we're doing this semester, and you guys have already passed that, so we're on to easier stuff. So you'll have 2 days to work on that, and then Friday we don't have school. Same thing tomorrow and Thursday. I'll just have a short Google quiz for you to fill out. Take as many times as you want. All right. Also want to remind everybody that's here for chemistry that the calorimetry lab is due next Wednesday, the 15th. If you have any issues with the calorimetry lab, shoot me an email. We can set up a time to work one-on-one. I also have that appointment booking thing that I keep linking in the posts. You can go on there, make an appointment, and I'll Zoom with you one-on-one so we can get it. All right? So let me just quickly go through the notes from yesterday, kind of review what we're doing, and then I'll do some practice problems. So over the last couple of weeks, we've been working on heating and cooling curves. This is like a graphical representation of how the temperature changes and the various states that we go through. So, you know, solid, liquid, gas. All right. So you've all seen the equation Q equals mc delta T. That's the equation that we were using before to find the energy involved. All right. So that's going to remain the same. Anywhere on the graph, we are changing temperature. So on my graph here, A, C, and E, the temperature is increasing. So we're going to be using the Q equals mc delta T equation. All right, so the temperature is changing. And remember, temperature is a measure of kinetic energy. All right, anywhere on the graph we have a plateau, so anywhere we have a flat line, so like B and D on this graph, we have a different equation that we use. All right, we're going to be using these equations off to the side. It's going to be the mass times either the heat of fusion or the heat of vaporization. The heat of fusion occurs anytime you go from solid to liquid, the heat of, solid to liquid or liquid to solid. So anytime we're transitioning between these two states, right here, and then the heat of vaporization occurs, we use that anytime we're going from liquid to gas or gas to liquid. Okay, so that's pretty much where we left off note-wise. And then we did some practice yesterday. I think I only had one person here. It was Nolan. Of course, he's not here today, but I understand you guys can't be here every day. So what I'd like to do next is go through some practice problems. These are very similar to what I did yesterday, and they're very similar to what's on the quiz. So let me pull my OneNote up. If you'd like to work these out with me, in your OneNote, under homework, you'll find the practice problems. These are the single-step curve calculations. If you don't want to do it with me and you just want to watch, that's fine too. All right, so let me make this a little bit bigger. So yesterday, we had a heating curve that we were doing our calculations with. Today, we're going to be doing the same calculations, but we're going to be using a cooling curve. So remember, heating curve, we're increasing energy. Cooling curve, we're decreasing energy. We're lowering the temperature. All right. So for the first question here, well, let me just point out a few things. So up at the top here, you see we have a table. Anytime we're doing these types of problems, you're going to be given some information. So in the question, or in the example up at the top, it gives us all of the C values. Okay, the C values are the heat capacities. So the heat capacity when it's a solid, a liquid, and a gas. That's all given to us. Right? Down below that, you'll see we have the value for the heat of fusion and the heat of vaporization. Okay, so that's all given to us in the question. The equations are also given here. Pretty much all you need is the Q equals mc delta T. You need the heat of fusion equation, and you need the heat of vaporization equation. All right, the first question that we're going to be working on says, calculate the heat necessary to change 15 grams of water vapor from 140 degrees Celsius to 100 degrees Celsius. Okay, so in the question, there is a lot of information, and there's a couple different equations. So like, how do you know which equation to use? Well, in the question, it's telling us that we're water vapor. So water vapor is the same as a gas. So we're not changing states. So on our graph, we're going to be somewhere where there is a diagonal. So on our graph up at the top, we know that we're going to be in this area right up here because we're a gas and it's a cooling curve. And we're going from 140 degrees Celsius to 100 degrees Celsius. So there's our change in temperature. So because we're not changing states, we're still a gas, we're going to be using the Q equals mc delta T equation. You use this anytime you don't change state. Don't change state. All right. So that's our equation that we're going to use. So the mass is right here in the question, 15 grams. The C, the specific heat value, since we're a gas, we're going to use the one on the table for the gas state, which is this one right here, the 2.0 joules over grams times degrees Celsius. So we have the mass, we have the C value. The only other piece we need on this equation is the delta T. So our delta T is the final temperature minus the initial temperature. So, well, the difference between the temperatures, rather. So the difference between our temperatures is 140 minus 100. So 140 minus 100, the difference between those is 40 degrees. Okay, so let's plug into our equation. Our equation is Q equals mc delta T. So the mass is given in the question, which is 15 grams. The C is 2.0 joules over grams degrees Celsius times the change in temperature, which is 40. Oops, I goofed. I had this right the first time. It should be final minus initial. So it should be 100 minus 140. So your temperature should be minus 40, because this should come out to be a negative number. The reason I know is because it's releasing the energy. So you're starting in the gas state and you're lowering the temperature, so you're releasing energy. So our final answer should have a negative number because it is releasing energy. Okay, so 15 times 2 times negative 40 is going to give us an answer of negative 1200 joules. So anytime you're trying to find the temperature, it should be the final minus the initial. All right, let me erase a few things here. Okay, the next question says, calculate the heat necessary to change 15 grams of water vapor at 100 degrees to liquid water at 100 degrees. And if I'm going too fast or if something doesn't make sense, please just type in the chat and I'll try to answer your question. Okay, so in the question, it's telling us that we're going from water vapor, which again is the gas state, to liquid water here. So we are changing states. So on our graph, we are right here. Since we're changing states and we're going from a gas to a liquid, we are going to use the heat of vaporization. So let me use a different color. So here on our equations, this is where you change states. All right. So the heat of fusion, the top one, is when you go from solid, oops, let me go back here. So the top one is when you go, why is this not cooperating? When you go from solid to liquid or liquid to solid, and the heat of vaporization is when you go liquid to gas or gas to liquid. All right, so we know that we're using the heat of vaporization. So that's going to be the mass times the heat of vaporization. In the question, it gives us the mass of 15 grams. So 15 grams times the heat of vaporization. In the table up at the top, it gives us the heat of vaporization. 2270 joules over grams. All right, so when we crank this out on our calculator, we are going to get 34050 joules. Okay. Now, we are releasing energy because this is a cooling curve, so this value is going to be negative. Okay. Next question. Calculate the heat necessary to change 15 grams of liquid water from 100 degrees Celsius to 0 degrees Celsius. So in the question, it's telling us that we are changing temperature right here, 100 degrees Celsius to 0 degrees Celsius, and we're liquid water. Let me try to stay consistent here. All right, so we need our delta T again. So our final temperature minus our initial temperature. So 0 minus 100 gives us a change in temperature of negative 100. And we're using the equation Q equals MC delta T. So again, we have 15 grams. Now, we're in the liquid state. So let's go back up to our table. Since we're in the liquid state, we are going to be using the C value for liquid. So 4.2 joules over grams degrees Celsius. Let me scroll back down. So 4.2 joules over grams degrees Celsius. Right? And we're going to multiply that by the change in temperature, which is negative 100. Right. So this gives us a value of negative 6,300 joules. Isn't this exciting? I'm having the time of my life here. All I can think about right now is how Sarah has cholera in OregonTrail. I really want to get back to that, but I don't think we'll have time today. All right, question number 4. Calculate the heat necessary to change 15 grams of liquid water at 0 degrees to solid ice at 0 degrees. So in this question, we are going from liquid to solid. So we're changing phases here. Since we're changing phases, we need to use one of the heat equations up here. So let me scroll back up to the top. So since we're going from liquid to solid, we're going to use the heat of fusion equation. So Q equals M, heat of fusion. So the mass, again, is 15 grams. The heat of fusion comes from our table. The heat of fusion is, go back up here. Our heat of fusion is 340 joules over grams. Okay. So 15 times 340 is 5,100. And since this is a cooling curve, this will be negative. So remember, cooling curves, you're releasing energy. You're going from an excited state, you're going from the gas state down to a solid. You're losing energy. And on a heating curve, you are gaining energy. So you're going from a solid state, you're getting those particles excited, they're moving around, they're going all over the place into the gas state. All right, we got one more left. Calculate the heat necessary to change 15 grams of solid ice from 0 to negative 40 degrees Celsius. Okay, so in the question, we know that we're in the solid state. And we're going from 0 degrees Celsius to negative 40 degrees Celsius. And again, we have 15 grams. So first thing we need is our delta T. Anytime we're not changing states and we're just changing temperatures, we're going to use the Q equals MC delta T equation. All right, so our change in temperature, so this is going to be final temperature minus initial temperature. And let's plug into our equation. MC delta T. So the mass is 15. The C value comes from our table. And we're in the solid state, so we're going to want to use the solid C value, which is 2.1. So 2.1 joules over grams degrees Celsius. And then our change in temperature, negative 40 degrees Celsius. So we get negative 1260 joules. It's pretty much what you were doing on the Google quiz. The only difference between what we did today and what we did yesterday was the fact that the graph today is a cooling curve and the graph from yesterday was a heating curve. So we were kind of doing everything in reverse today, right? The only thing you have to watch out for when you're working with these, okay, if you're a heating curve, let me try to make this a little bigger. All right, so if you're a heating curve, you start in the solids. Let me try to get a different pencil here. Okay, so if you're a heating curve, you're starting as a solid, then you move to a liquid, and then you go to a gas. So here and here, between the states, is when you have a phase change. So again, heating curve, you're starting at a solid, then you go to liquid, and then you go to the gas state. Okay, so you'll see the curve it's moving up. When you have a cooling curve, like what we were working with today, it's the opposite. So you're starting as a gas, then you're a liquid, and then you finish up as a solid. So between the states is where you have those phase changes. So when you have a cooling curve, you're going gas to liquid to solid. And there you go. What questions do you have? Is anybody still paying attention? Guess we don't have any questions. All right, Daniel says we're good, so we're good. Just want to remind you before I sign off here, our Zoom check-in is going to be on Thursday instead of Friday this week. It's going to go from 1 to 2. I only had a couple people show up last week, which is fine. We went through, and I got a whole list of TV shows that I need to catch up on. So that was good. It was very productive. It was a very productive Zoom meeting. But our Zoom meeting this week is going to be on Thursday instead because we don't have school on Friday. And it'll be from 1 to 2. So if you could, show up. You can do it on your phone. So while you're out enjoying the wonderful sunshine that we've been having over the last couple days, just bring your phone out and just catch up with your friends. So that's the plan. It was nice seeing all of you on YouTube today. If you have questions, shoot me an email. Otherwise, I will see you guys tomorrow. Yeah, so Daniel, if for some reason when you're going through that it doesn't make any sense, just shoot me an email or book an appointment on my booking thing, and we can go through stuff, okay? Don't worry about it too much, right? I know you guys got a lot on your plate right now, all right? I've been trying my best to try to make everything manageable for you guys so you're not overwhelmed with the amount of work that we have. There's really not much for each lesson. I know that there's a lot going on the outside world. I have a lot of students that are working jobs. They've got siblings to take care of at home. All right, this is not something anybody could have seen coming. So I get that there's a lot going on at home for a lot of people. So as teachers, we're doing the best that we can to try to make things manageable while still moving everything forward, okay? So certainly if anything comes up, let me know where you need help or, if something at home's going on where you can't stay current with everything, just let me know, okay? But anyway, I'm going to go ahead and sign off. It was great working with you guys today. I will see you tomorrow, and